Hey there, welcome back. I'm Chili, and this is episode
11
of the HUGS series. Today we're going to make an audio system. We're going to make it using XAudio2 because that's what I chose. Now, first things first, let's go back to principles. What the fuck is sound? So let's say you got a speaker. That motherfucker's got like a voice coil. Not a voice coil, it's got that too, but it's got a speaker cone. And when that speaker cone moves, it is going to crush a bunch of air molecules together. And those air molecules are going to be like, step back, you're dancing kind of close, I feel a little poke coming through on you. And what I'm trying to say is when you compress like some gas, its natural tendency is it's going to want to spring back. And when it springs back, it has momentum, it keeps going in that direction, and it compresses the surrounding gas molecules over here. So after this springs out, this becomes sparse, and this part becomes dense. And then the same thing happens, crunch together, and then they're going to fly apart and crunch together the neighboring ones, and that just keeps oscillating and propagating through space until it hits your ear. Vibrates your eardrum. It goes through, I think there's like 3 bones in your ear. The wishbone, the funny bone, and the bone zone. And then that gets translated by some nerves to signals that your brain understands. And that's how sound happens. Bibbidi bobbidi bo. Now, I was at like there was some party thing at the company I work, a 50th anniversary or some bullshit like that. And I banged my arm on the table. And everyone was like, I felt like my hand was like melting off, the skin of my hand was melting off the bones. It was like burning so bad because I hit my funny bone, right? And they were looking at me like I was retarded, like, holy shit, what happened? And I said, because I forgot the name of funny bone in, like, how you say it in Japanese. And I was like, whatever. I'll just cry myself to sleep. Anyways, what was I talking about? Oh yeah, so that's sound. It's just pressure modulation or oscillations in pressure through some kind of fluid, specifically air, but it works in water too, right? Now, if you want to represent that graphically, mathematically, probably use a graph like this. So this would be time, and this would be pressure. So the midline here is the ambient pressure, the equilibrium in the atmosphere, the room that you're in, and then this is going to be the pressure at a specific point. So if you take a fixed point, say this point here, this is the pressure at that point over time. I know it looks on this graph, it looks like this is the pressure through space, but if it were the pressure through space, if that were the actual case, then it would actually look something like this. Because, as we know, sound attenuates as you travel away. It's the inverse square rule, right? Same thing for light. But that's another story. Who the fuck cares? Sound, it's like this. It's a motherfucking wave. Now, another more interesting question is how the fuck does that work on a computer? Because as we all know, because I've said so, everything on a computer is a motherfucking number. So how does this translate into numbers? Well, what you do is you capture the pressure value at specific points in time, and that's called sampling. And you turn those values, you have to determine what is the maximum value that I'm going to accept. And then that will be, if you got a 16-bit number, then that maximum value will be like 65, 5, 35, or whatever. I don't know. And this one will be 0. Or maybe you want to go, this is 0 and this is positive 32 32,000. This is negative 32,000. I don't know. It doesn't matter. What matters is that you're going to turn these analog values into quantized digital values. We generally use 16-bit. 8-bit was more common back in the day, but it sounds like ass, so we use 16-bit. You can use 24-bit, but that's just going overboard. Now the other question is, how often should we sample the sound? I mean, obviously you're going to want to sample it more than once a second. How are you going to make sound waves if you're only sampling one pressure value per second? But what is the optimal rate at which to sample? Well, a guy named Nyquist, he answered that question. Basically, if you want to represent a signal with a frequency of f, your sampling rate must be 2f. I'm not going to go into the reason why, but that's the way it is. Now, humans generally hear from about 20 hertz to about 20 kilohertz. So that gives us a sampling rate of about 40 kilohertz if we want to reproduce 20 kilohertz sounds, sine waves. So that is pretty much very close to what we get for, wait, why did I make that a period? Anyways, for what we have for CD audio, right? 44K is what we use for CD audio. These days, graphics cards also very commonly 48 kilohertz. And that's basically all you need. Any more is really overkill. It won't make too much of a difference. But anyways, that is how you represent sound in a computer. Just a bunch of numbers here. So this, for example, this, it's called pulse code modulation, really. And, for example, this waveform, you might represent that as a series of values like 65, 5, 35, and then the next one might be like 60,000, and then the next one might be like 30,000, and then the next one is like 0, and so on and so forth. And if you got stereo, then you've got 2 of those, so you've got extra values, whatever. That's how it works. The question now is, how is that translated, how is that digital representation, this string of number, actually turned into sound waves that you can hear? And the answer to that is, well, you got a speaker. I don't know if you guys know how a speaker works, but like I said, you've got the speaker membrane, the what do you call it? The voice, not the voice coil, the cone, speaker cone. And that's what does the compressing of the air. Now you need something to move the speaker coil. So basically what you've got is you've got a permanent magnet here, and then you've got a coil here. So as you know, when you pass a current through a coil, it creates a magnetic field. And if you've got a permanent magnet with a magnetic field, the two fields interact, and the coil is going to move back and forth in response to the voltage across the terminals of the coil. Voltage induces a current. Current induces a magnetic field, which creates a force, which moves the coil. Coil is connected to the speaker cone. The speaker cone moves, and sound is emitted. All right, so you want a voltage going across here that's the same as the sound wave that you want to produce. So what you need is a device which takes the the numbers 65, 5, 35, 30,000, blah blah blah, takes these numbers in and outputs a voltage to this. And that device is called a digital to analog converter, DAC. It's very simple. You can make it out of resistors and stuff if you want, although it would be a pretty shitty one, I guess. I don't know. Anyways, so you've got a DAC. So to make yourself a really shitty sound card, all you really need is you need your that's an O. That's not an A, that's an O. You need a DAC, you need an amplifier, and then that will go out, to your speaker. That's a really shitty diagram for a speaker element. I don't even know. No, you can never tell that was a speaker. I don't know what I'm doing. I think I'm. There you go. That's a speaker. That makes a lot more sense. So you got digital analog converter. You got an amplifier. You got a speaker. So you hook this up with just a register, and then you got your CPU, and it can change the value of the register at a specific timing. For example, every 20 microseconds will give you about 44 kilohertz, or like 40 kilohertz, I forget. Yeah, 20 microseconds will give you 40 kilohertz or something like that. And there you go. You've got audio out. The problem with that is now you've got your CPU. It's got to make sure that it continuously updates this value at fairly exact timing. Like every 20 microseconds. That's like a really needy knob right there. It's going to waste a lot of time just waiting for the exact moment to change the register value before it can work on other shit every 20 microseconds, especially back in the day when CPUs were a lot fucking slower. So to solve that problem, we make our system a little more sophisticated. Instead of having a single register to store the value that is converted to analog, we make a buffer, which is, just an array of memory values, or an array of registers, if you like. And so now what you have is the CPU can fill the buffer with, a bunch of different samples. And then the sound card is going to have like a counter and a timer. Timer hooks up to the counter. The counter basically controls what memory location is used to get the digital value for the digital analog controller. So the CPU fills up the buffer, and then the video card just plays the values in the buffer, cycling through all the values. Once it plays a value, the CPU can then fill that location with a new value. So you can queue up samples, and that will allow you to, queue up maybe like, 1 millisecond worth of samples into here, and then you're good for a while. You can go do a bunch of other bullshit, as long as you come back every now and then and keep filling the sound buffer with new samples. And that's basically how sound hardware works today. Now you might ask yourself, or you might ask me, well, why don't you just make why don't you make this buffer here like really fucking big? Like just make it like 128 megabytes. And then your CPU can do other stuff for like a real long time and doesn't have to worry about filling the buffer. It only has to fill it every so often. But you can't make the sound buffer too big. And the reason for that is delay. If you have a sound buffer and you fill it with a bunch of values, and then the sound card starts to play those values. So let's say the next value is going to go here. That means that when an event happens and you want to put that in the sound buffer, it has to go in the next available spot, right? It has to go here. But there is a delay between when the event happens and when the event is actually played. And that delay is based on the size of the buffer. Bigger buffers mean bigger delay. So you don't want your buffer to be too big. But if the buffer is too small, you'll have the problem where the buffer is starved. The CPU fills the buffer, then goes to do something else. And before the CPU has time to get back to the buffer, it's empty. And the sound cuts out. And then when the CPU comes back, it puts some more in, the sound plays, it cuts out, it plays. But it does this very quickly, so it has this like horrible sound, like like just demons from hell. I know this because the first computer I ever had was really shitty. And like whenever you would, like if you're playing like an MP3 file and you went to scroll in Internet Explorer, they would make that sound because the sound buffer would get starved just having to scroll the screen in Internet Explorer. The CPU wouldn't have enough time to fill the buffer, and it'll make that sound every time you scrolled. It was horrible. So you need a good balance in your sound buffer size. All right, what else do I want to talk about here? Let's go back to the docket. All right, so I talked about Bing. Oh, okay, yeah, fuck you. Talked about how sound works, talked about how it's represented digitally, talked about how you go from digital representation to physical sound. This was all like just the background of sound that I wanted to go over because I thought it was an interesting topic. Now, let us skip on to the architecture of XAudio2. Oh, one more thing that I wanted to just talk about quickly before I move on because it's salient. So the job of filling the buffer, making sure that the buffer doesn't starve, you could do it in, let's say, like a poll style, where like in your main message loop where you check for Windows messages, and then you call game.go or whatever in our framework. Somewhere in that loop, you could also call sound.update, and that would fill the buffer. And that would work fine, except if the frame rate dropped, you would have the problem of the sound buffer getting starved again. So your sound quality would depend on your frame rate, which is a kind of a shitty setup. So what we generally have is what's generally done is you spawn a new thread. And that thread is what is in charge of moving data into the sound buffer. And so that happens in the background in parallel to whatever else you're doing, your graphics bullshit and all that good stuff. So threads and audio go hand in hand because it's a small task. It only takes a very little amount of CPU power to keep a buffer full, but it has to be done very frequently. You do a little bit of work and then you take a little break and then you do a little bit of work. So this is the kind of stuff that you want threads for. All right, I just want to say that. Now, XAudio2 architecture. How does it work? All right, so this is how the basic XAudio system is going to work. You have your buffer of input audio data. This is what you load from your WAV file, from your fart.wav. And that is passed on to a source voice, which is in turn passed on to a mastering voice, and that goes to the audio device. And that's all it is. It's a very basic system when you think about it. Now, in general, in a game, you're going to have multiple voices mixed together. So you have multiple source voices, and then you have one mastering voice, and it's the job of the mastering voice to mix all the source voices together, basically to add up all the pressure values of the samples before it's passed on to the audio device. So if you wanted to play, for example, 4 sounds at once, 4 different sound effects at once, you're going to need at least 4 source voices. Now there can be more to this system. This is a very basic overview. You can have a situation where you've got like source voice, and they go into a submixing voice, and that then goes into master, and you might have another source that goes directly into master. You can have a situation like this, and they can have attached to them, like effects that can, like reverb or whatever, audio effects that can affect the way the sound is processed. But we're not going to get into that right now. Our basic situation is like this, or like multiple source voices going into the mastering voice. Now, the way the workflow works for XAudio2 is, first, you've got to create the whole system, the whole shebang. It's like in DirectX, you got to do DirectX create or Direct3D create. Here you got to do XAudio2 create or whatever. I forget what it's called. So you do that. Then you've got to create your mastering voice, and you got to create your source voices. And these are the things that are going to be processing the audio for you. Each one by itself is going to have its own thread associated with it that does the processing. So creating these things creates the thread and other stuff that's going to be useful. Then what you do is you got to load some kind of audio data. So you're going to load it from, pew.wave. Load that into a buffer, and then submit that, give the source voice a pointer to that buffer and some information about how the buffer is laid out. And then what you do is you call start on the source voice. Start. And that signals this thread to start processing this data and passing it on to the mastering voice to be mixed together and output. Now you can actually submit multiple buffers. So I can submit one buffer here and tell it to start, and it'll start processing this buffer. But I can chain together multiple buffers, and what it'll do is it'll process. When it hits the end of the buffer, it'll seamlessly start processing the next one. So you don't have to give it all the audio you want to play at once. You can give it chunks. You can stream chunks of audio samples to the voice, and it will be able to play them seamlessly without any gaps in between. That's how it works. You queue up buffers for it to play. Now this is the thing that actually plays the audio, that does the processing, is a separate thread. So it does its own thing. It's running in its own world. But what it does is it can communicate with your application, with your code. You can configure it by supplying callback functions. So there's a class, and it has a bunch of callback functions that you can override, and you can tell it the behavior that you want it to do at certain events. So one of the events is buffer end. So whenever it hits the end of a buffer, you can tell it to do some bullshit. Or stream end, whenever it hits the end of the last buffer that's queued up in the stream, you can tell it to do some bullshit. Another thing is loop end, if it hits the end of a loop section. And there's other ones I forget. The only one I ever use in our system is buffer end. So we'll get to that later on. But yeah, that's how you can configure how the thread works. All right, so that was the basic architecture of XAudio2 and the basic flow of how you can set it up and play a sound. Now I'm going to talk about an overall implementation, system architecture. I'm going to talk about a system that you might naively try to create and why it doesn't work properly. All right, so let's say you've got a system where you've got 3 sound effects that you want to play. And so what you do is you create an object. We'll call it sound. Fuck. That was wrong. Sound. And it encapsulates the buffer data and the source voice. So you've got one source voice. It is constantly bound to one buffer data. And when you want to play that sound, you just call, let's say this sound is fart. You call fart.play. And it'll play this sound. That's fine. Except what if you have the situation where you've got multiple farters, and so one object, one farter, makes a fart sound, and then maybe 2 or I don't know, like 50 milliseconds later, another object now makes the fart sound. Well, a voice can only play one audio buffer at a time. It can't mix together two different audio buffers. So if you play with this guy, and then soon after you play with this guy, that is going to cancel this one, and you're just going to play from the beginning of the file. Either that, or if this one is already playing, you just have to ignore this one. So either way, it's not a good situation. You want there to be multiple instances of the same sound to be able to play at the same time. Now this doesn't let you do that. Now you could, for example, quote unquote, solve this problem by, creating, for example, one instance of the fart sound for every farter. But that wastes a lot of memory, right? Wave audio data takes up, a fair amount of space in memory. So creating one for every farter is not a good idea. So you could do one better than that. You could say, okay, well, we only need one copy of the audio data, but what we're going to do is we're going to create multiple source voices inside of our sound object. And that way, if someone calls play, it'll use the first source voice that's idle. And then if another person calls play, it'll use the next one that's idle. And it'll just scan through, your array of source voices. And that is a better idea. But think about it. You have to do that for every single sound that you have. And that is a lot of voices. And every voice has its own thread. Now, they'll be idle most of the time, but they're still going to take up resources. And it's still going to be a big waste, because you're probably not going to have, 10 of every sound playing all the time. That would just be cacophony. Most of these voices are just going to sit around idle and just wasted. So the system that I propose, and the one that I've developed, is this one. So you've got a sound system, and that encapsulates, your XAudio2, like your device, your system instance, and it encapsulates your master voice, and it also encapsulates a bunch of source voices. And these source voices are organized into two vectors. One is the idle channel vector, and one is the active channel vector. So to start off with, all of your source voices are in the idle channel vector. And when you want to play a sound, what you do is you bind that sound, the sample buffer for that sound, to one of the idle channels, and you move it into the active channel vector. And now you have a relationship between that channel, which is just basically a wrapper around a source voice, and that audio buffer, which is going to be a sound class. So every sound is going to maintain a list of pointers to all of the channels that it is currently playing on. And every channel is going to maintain a single pointer to the sound which it is currently playing. And in this system, you only need a number of channels equal to the maximum amount of simultaneous sounds you ever want to play at once. So, it doesn't have to be that big. You can go 64, and that'll be way more than you probably ever need, depending on what kind of game you're doing. But the beauty of it is you don't have a lot of wasted channels sitting around, you don't have a lot of wasted space, and you can play a single sound many, many times without any problems. So this is the system that I have developed for HUGS, and the one that we'll be using. It has three main classes: the sound system class, the channel class, and the sound class. Now, sound system, the channel class is actually internal to sound system, so it's not I mean, the sound class also knows about it, but the client of the API, the actual HUGS engine, doesn't really deal with channels directly. It only deals with the sound system and specifically with sounds. It'll call sound.play, and sound.play will tell sound system, I want to play myself, and sound system will find it a channel to play on that'll create a relationship between the sound and the channel and move the channel into the active channels list. Now, when an active sound finishes playing, the callback function, so the thread that's playing it, will call the callback on buffer end, and that will call functions in sound system to move the channel back into the idle channels, and it'll call functions in sound to tell that sound, okay, I'm no longer playing on you, so let's remove this relationship. Yeah, that's it. That is how the system basically works. 3 classes. All right, let's take a look at the code, shall we? What do we got here? All right, hope no porn showed up there. There we go. All right, so I created, of course you have to synchronize with the GitHub, and then you can create a new branch called sound. And we'll just take a look at the sound branch right now. The view history. So I made a lot of commits to this one because I did a lot of work on it. But more or less all we're going to talk about right now is just the very first one, which is where I created the base of all of the sound system. And in the next episode, we're going to talk about all the other bullshit I went through to refine the sound system. But today we're only talking about the main gist of how it works. So let's take a look at, I created another branch here. This branch, it doesn't exist on the GitHub. It's only local. I created it here to take a look at the sound system at this point. So let's check out that branch instead. So we'll go branches and butt plugs. Here it is, unpublished branches, butt plugs. And here we have the sound system. All right, so where to start? That is the question. I guess we will start in the sound system proper, the main class. Now we've got some classes here for errors. They're exception classes. We can forget about them. We'll talk about them. Talk about those in the next episode. And the channel, we will talk about that soon, but not right now. Let's just talk about the sound system first of all. So what have we got? All right, so we've got the constructor of the sound system, which is actually private. And we'll get to that in a second. The main reason it's private is because we're using the singleton pattern. So we only want ever one instance of the sound system to be present. And so one way we can ensure that is making the constructor private. And the only way that the sound system is constructed is actually in this static function sound system get. So this gets a reference to the sound system. And if we just quickly toggle over here, what get does is it actually has a local static variable here, which is the sound system, the instance. And this will only create the sound system once. The first time you call get, it will create the sound system. We'll call the constructor. But every time after that, it will skip the construction, and it'll just return the instance that has already been constructed. So this is a neat little pattern you can use to implement the singleton pattern, right? A neat little implementation you can use using local static. I forget the term for this kind of static, but maybe it's local, I don't know. You declare it inside of a function. So this is where the system is created. Now, what happens when it's created? So we've got, let's go back. Where's the constructor? Here it is. So the constructor here, it has to initialize COM because XAudio2, the engine, that's the whole system. It's like when you call Direct3D create. The engine is a COM object, so you have to call initialize COM to make sure that COM system is working. And here we just set up the format of the audio samples, the audio data that we're going to want to support. So for the current system, we only support one format at a time, and this is setting that up. So how many channels, sample rate, and bits per sample. Those are the mostly the important parts here. So we set up the format, we initialize the format structure, and then we call XAudio2 create. We create the engine. We use the pointer to the engine to create the mastering voice. Now the engine is a COM object, but the rest of the objects in XAudio2 are not COM objects. That's important to know because COM objects, you have to call release before you don't destroy them, you call release on them, right? And so you only call release on the engine. You don't call that for any of the other parts of the system. So you create the mastering voice, and then here we create the channels that I was talking about before. So we have a vector of unique pointers, here the idle channel pointers, and yeah, we just push the unique pointers into our idle channel vector. And the constructor for channel just takes a reference to the sound system. But we'll talk about that in a little bit. Let us return. So that's the constructor. What else have we got? Well, we can look at the data. Here all we've got is a constant telling us the number of channels that we support here. Pointer to the engine, pointer to the mastering voice, wave format EX structure that determines what format we're supporting, and two vectors, the one that holds the idle channel pointers and the one that holds the active. So as we use our system, as we play sounds, the idle channel pointers will be moved into the active channel pointers, and when they finish playing, they'll be moved back into idle. So they just move back and forth. The voices, or the channels, move back and forth between these two vectors. Now they move based on two functions, play sound and deactivate channel. So what play sound does is you pass it a reference to a sound object, which we haven't talked about yet. And what it does is it checks to see if there are any idle channel pointers in the vector, and if there are, then it removes an idle channel pointer and puts it into the active channel pointers thing here, and then it tells that moved channel to play the sound that was passed in. That's how play sound works. Deactivate channel, which is what is called when the channel has finished playing, what it has to do is it has to search for, where is it? So we do find if, so it searches the active channels for a specific channel, and when it finds that one, it returns an iterator to that channel, and then what we do is we move the pointer from that, what is it called, that unique pointer object. We move the pointer to the idle channel pointers vector, and then we erase that unique pointer object from the active channel pointers vector. So again, it's basically just the opposite of this one, only it's a little more complicated because you have to find the channel in the vector first before you can move it. All right. And that's basically it for the sound system. There's not too much else here to note. I mean, the destructor here, this one just calls reset on all of the what do you call it? It's the unique pointers. It releases all of their dynamically allocated memory, which calls the destructors for every, what's it called, channel object contained therein. And then we release the engine, and finally we uninitialize COM. No big deal there. Now, I wonder, what should I talk about first? The channel or sound? Sound, well, most of it looks big, but actually most of it is just in the function that loads the wave files. So let's talk about channel first. Like I said before, it's internal to sound system. Actually, I thought I made it private, but it's actually public. Maybe that is because I need to use it in sound. Probably. Alright, makes sense. So it's internal to sound system. The constructor for channel, it creates a static instance of voice callback. Now, voice callback is an object, but it has no data associated with it. It's just an object which holds a bunch of virtual methods that you can override to specify behavior of the callback, the thread for the channel. You can specify what the channel thread does when certain events occur. Now, most of these events here, you can see I just specify them with empty brackets, so don't do anything. The one that I do specify is on buffer end, and that is when the buffer that we have submitted is finished. And we'll talk about that in a second. But yeah, so we only need one copy of this because the data, there is no data. It's all just function pointers, basically. And so what does the channel actually have? What kind of data does it have? Let's see if I can here it is. So it has XAudio2 buffer, and this is just information about the buffer of samples that are to be played. And mainly all it holds, the main thing it holds, is the pointer to the samples and the number of samples. But it can also hold information about looping and other bullshit. Mainly it's just about holding the samples. Well, it doesn't hold the samples themselves, but it holds a pointer to the samples. And you've got a pointer to the source voice. And here you have a pointer to sound. This is what I was telling you about before when you create an association between the channel and the sound that it's playing. So this pointer holds the pointer back to the sound that we're currently playing. All right. So the main functions are play and stop. And then, of course, the callback function here. Where is it? On buffer end. So let's look at play then. Toggle header file. We'll go back down here. And we got channel play. So it plays a sound. And what it does is, first thing it does is it says sound.add channel and reference to this. So that gives the channel basically it allows the channel to hold a list of, not the channel, wait, fuck, I said it wrong. This allows the sound to hold a vector of pointers to all the channels that it is currently being played on. So it can keep track of what channels are currently playing it. So that's the first thing. Tell the sound that I am playing your sound. And then set our pointer to point to that sound. So this sets pointers going in both directions. Bidirectional association there. Next, we set our buffer. These are the two important parts of the buffer. We set our buffer pointer to point to the audio data of sound. Now we can do this because in sound, let's toggle header and code file. In sound, we declare sound system channel as a friend. So that is why we can access its private parts. So we get the pointer to the block of sound data, and we get the number of bytes in the block. And that sets up our XA buffer structure. Then we submit the buffer structure to the source voice. With this, we just give it a pointer to the buffer. And then we call psource.start. And that will signal to the thread that it can begin to consume the data in the buffer that we submitted. And that's it. Now the thread will start to run. Next, what is the... Well, I guess we can talk about stop. Where is stop? It's up here somewhere. So stop is very simple. We just call stop on the source, and then we call flush source buffers. And I think you have to call both of these for it to stop the current one it's playing. I'm not sure. Or if you call stop, it will still keep the buffer, so you can call start again. So we want to, when I say I want to stop a sound, I want to stop it, and I want to flush the buffers so that the buffer ends. And the reason is because buffer end is the thing that will move our channel from, or will cause our channel to be moved from active into idle. So when you stop a buffer, or when you stop playing a sound, you want that channel to move back into idle so that it can be used again for a different sound. Whew. So what have we got here? I guess the next thing that we want to talk about is this callback on buffer end. This is what happens when a sound stops playing, either because we reach the end of the sound or because we've called stop and flush buffers. And that is here. So sound system channel voice callback on buffer end. And it takes a pointer to a context. Now that context is going to be a pointer to the channel object. So here we just cast that to reference to channel to make our life easier here. So we don't have to cast it every time we want to use it. Now, the way that this pointer gets determined is, if we toggle header and code file, when we create the source voice, well, it's not passed in here. It's actually passed in through the buffer that we submit. So for every buffer, you can give it a different context pointer. But we just set the context pointer to the channel, and we leave it the same there for the duration of the channel's life. So that part never changes. The only thing that changes in the XA buffer is the pointer to the data and the number of bytes. So anyways, it gets the this callback will receive the pointer to the context. That's its life thread, its thread back into the part of the code that we create. And that allows it to access the channel object. So what we do is we call channel, and we use its pointer to the sound to remove the channel from the sound. So we say that we have finished playing your sound, so we are no longer playing your sound. Please remove us from your list of channels which are playing your sound. So we call remove channel on the sound. Then we set our pointer to the sound to null, because we're no longer playing that sound. We don't want to refer to it. So we remove that bidirectional association here. And then we call soundsystem.get, so we get the sound system singleton, and we call deactivate channel, which, as I've explained before, will move that channel from the active vector to the idle vector, so it can be ready to play a different sound. So on buffer end removes the bidirectional association between the channel and the sound, and it tells the sound system, or it calls the function in the sound system to move the channel from active to idle. And that's it. So that is the main system for all of our bullshit with sound. The channel and the sound system. Now, the last part of this this bullshit fiasco is the actual sound class itself. This is the thing that encapsulates the sample data, the wave file that you load. So when you load the data from the wave file, it goes into a sound. All right. So besides the part of the sound that's loading the wave data, which actually takes a while, it's very simple. It has a play function, and all that does is it calls the sound system.get, and it tells it play me. So it passes a reference to itself. And here we have the remove channel and add channel, and these are called by the callback. Are they called by the call? Remove channel is called by the callback, right? So this is the thing that's called when we reach the end of the buffer. And it tells it, remove me from your mailing list, please. Add channel is called when we call channel.play, I guess. Where is it? Yeah. Play. Let's go back here. We'll call add channel. All right. So this is known. This is very simple. Just add to our vector or remove from our vector, one or the other. The destructor, what it does is it stops all of the channels. So it tells all of the channels that are currently playing it, don't stop playing my sound. And then it waits until the active channel pointers, so the pointers to the channels that are currently playing it, it waits until it is 0. So while it is greater than 0, it just keeps waiting here. Now, the reason why you do this is because when you call stop, that doesn't immediately stop the sound. Remember, the sound is being played on a separate thread. So when you call stop, you send a message to that thread, but it might take a while for that thread to get the message and to respond to it. So you can't immediately destroy this data, because if you destroy this data while it's still being played, you're gonna get an exception. You're gonna get a memory fault. So you tell all the channels that are currently still playing you, stop playing. You wait until they actually stop, and then you can leave the destructor and destroy this data. I don't think I've talked about this before, but you can actually, there's a template specialization for unique pointer, and you can have it own an array of data. So here it owns an array of bytes. And the way that works is, well, we'll get to that. That's in the constructor here. So here is where all the bullshit happens. This is where we load the data and parse the data for the wave file. Now the old system I had for direct sound wasn't that great, and it kind of puked on different wave data, but I think this one is better. So for any of you who are going to be using this, try using different wave files if you want, and let me know if you find some that just don't work, because I believe that this one is probably going to work with more wave files than the old direct sound code did. It doesn't have anything to do with the difference between direct sound and XAudio. It has to do with the way that the algorithm or the routine that I use to load the wave files. So first thing we do is what? Create a unique pointer of bytes for the file that we're going to load. And what I do here is then I open the file, and I open it in binary mode. We don't want to open it in text mode, because text mode does a bunch of processing, first of all, with the data. and it will remove certain characters and reinterpret them, and that's bad. So definitely, if it's not a text file, don't open it in text mode because you'll just fuck yourself over real bad. So we open it up, and the first thing we do is we read the first 4 bytes, and those first 4 bytes have to be RIFF, backwards because of big endian or little endian. I forget which one. You know how byte orders work, because I don't. And so we check to see if the very first 4 bytes match what we are expecting, which is RIFF. That's the type of file that we are expecting. If they don't, we throw an exception. Otherwise, then, we check the next 4 bytes. They represent size of the file. Specifically, the size of the file after this point, not considering the 4cc code and the size value. So that's a point that will become important a little bit later, but not in this episode. And we just check to make sure. We do a small sanity check. Like if it's less than 16, we definitely know that the file is way too small, and we throw an exception. Otherwise, we seek to the beginning, and then we create a new memory block with make unique equal to the size of the file, and we load the data from the file into that memory block. So we do file read, and we read it into the memory block that we created with make unique. So with make unique and with the array brackets after the value type, you can create a block of size n. You have to pass it. In this case, you don't pass make unique the constructor values. You pass it the amount of elements you want to create in the array. So what I'm trying to say is make unique. You can make an array with that shit. Anyways, moving on. So I create I load all of the data from the file into memory. I do this so that I can do random access. Otherwise, I'd have to use seek all the time. It's not a big deal. The original code actually used seek. So I just decided I'll just load the whole goddamn thing into memory. Now, the next thing you want to do is you want to check, the next 4 bytes. So these are the first 4. These are the next 4 after that. And the next 4 after them, they have to say wave, because we're looking for a wave file. We're limiting ourselves to loading wave files. So we make sure that we have a wave file. And next comes the fun part. Because after these 3 parts in the wave file, these 3 are always in this order. But in a wave file, in general, the chunks, the parts of the wave file, like the part that tells you how many samples per second, or how many bits per sample, or how many channels, the format header, that's one part of the file. The other part is the actual data, and they can be anywhere in the file. They don't have to be in the normal order. Normally your wave file looks something like this. You've got the first 3 or the first 12 bytes, like I told you before. The RIFF code, the size of basically the whole thing after this point, and then the format, which is going to be wave. Now after that, you've got the subchunk 1, which is your format subchunk, and it describes basically what kind of sound information the file contains. And then you've got subchunk 2, and that contains the data, the actual samples of the sound. This is how it normally works, but it doesn't have to work like that. Different files can mix it up. They can mix and match. They can get all funky on you. And I think that was why the direct sound routine puked on certain files, because it just assumed that this stuff was in this order. But it actually can be in different orders. So first thing you've got to do is you've got to search for the format subchunk. You've got to find out where it is. So the way you do this is we set I which is index into the data of the file, equal to 12. So that is right here. That's the address or the index of the subchunk 1 ID. So there is going to be a subchunk in here. It could be the format, it could be the data, it could be something else we don't even know. So what we've got to do is we've got to check to see whether it's the format. If it's not, we've got to skip to the next subchunk. Because although subchunks, they can have different sizes and all different setups, the first two parts are always the same, the ID and then the size. So if you can use the ID to see if it's the chunk you're looking for. You can use the size to skip past to the next subchunk if it's not the one you're looking for. And that's what we do. We check to see if it's a format chunk at, p file. Whoa, fuck that. So we check that thing, see if it's format. And if it is, we copy the data from that subchunk into this structure. And then we set our flag that we filled the format equal to true. And then we break, which allows us to skip out of this for loop. Now, if it's not true, what we do is we increment I basically by the size of, where is it? By the size of this subchunk. So we tell I, okay, you've got to go to the next subchunk. So we use this subchunk 1 size value, which is here, right? If I is the subchunk ID, I plus 4 is the size. So we get that value. We add 9, which is, we add 8 because we have to add the 4 bytes for the size entry itself and 4 bytes for the subchunk ID. And that will take us from here to here. And then we add an additional 1, and we bitwise AND with this value in order to make sure that we are on a word boundary. So if the data size was of like a weird size, an odd number of bytes, this will bring it up to an even number of bytes. It's just an extra word padding count. It's a cute way of calculating word padding without using like mod. So anyways, we either load the data and set a flag, or we skip to the next chunk and then do the test over again. Now, when we leave this for loop, we've either left it because we've loaded the data, or we've left it because we've reached the end of the file. So to check which case that is, we check to see if we've filled the format by checking this flag. And if we have not filled it, we throw an exception that says we reached the end of the file, we didn't find the format chunk, we're fucked. Now, once we've done this, we want to make sure that the format of the file that we're trying to load matches the format that we set up our sound system with. Remember, the sound system, the constructor set up a wave format EX structure, and that states that this is the format that we're using. We've got to make sure that all the files we load match that format. So here we just test all of the members, all the important members of the structure, and we make sure they match up with the ones that we initialized our sound system with. And if not, we throw exceptions with appropriate text. The next thing we do is we do the same thing, but we look for the data chunk. So it's the same shit, different pile. And once we have found it, we create a buffer to hold the data, and we store the size of the data, the number of samples, or the number of bytes, not the number of samples, number of bytes into the n bytes, which is a member of sound, and we copy the data from our file buffer to our sample buffer. And again, we set our flag, and we do the same bullshit. And then we're done. And that is how sound is loaded. It's not that complicated. This part's a little weird, but it's not that weird. This has got some weird like casting bullshit. Because, see, if you use single, what is it called? Single quotes here, you can treat characters as an int, which is interesting. But anyways, that's how you compare bullshit and how you load a WAV file. All done. All right, Jesus Christ. That took, well, about as long as I expected, but still longer than I would have preferred. But that is how the sound system works. You load up some sounds, and you play them on channels. That is all I have to say about that. Let's see here. Maybe I can build this and run it and see if it works. We'll run it in release. Didn't work. All right, well, let's run it in debug then. All right, so we got a bad 4cc code. Bullshit. I think I know what the problem is. And the problem is that the file that I'm trying to load doesn't actually exist, because this file is not in the folder right now. So what we're going to do is we're going to look and see what files are in the folder, and we're going to load one of those. Open project folder. Where are my WAV files? I don't have any WAV files in the folder at this point. That is disappointing. 1 second. All right, I have pasted buttspin into the folder. Let's try that again. All right, if you can hear that, because it's like super loud, it has loaded the sound. Beautiful. All right, so that is all. I mean, here's how you use it. You create a sound object, you pass it a string, and then you call play, and that's it. You create a sound and you play it, and it plays, and that's it. In the next episode, we'll talk about a bunch of bullshit details that have to be talked about, refinements on this general idea, and how to make a sound effect system that actually sounds good and not like ass. But until then, I am Chili, and I think I'm done for today. Please, if you have any questions, this was a kind of a complicated topic. I hope I covered everything, but I might have missed something. Feel free to leave a question. You can ask a question in the comments, or even better, you can ask a question on the forum. And if you like the video, please press the like button. It helps me out a lot. And that's it. Later.